For this lesson, we're going to continue going over the BJT circuit analysis, but for this lesson, we're going to focus more on the AC analysis part of the circuit. So we're going to take the BJT circuit and actually implement the AC equivalent model. Now, in this particular lesson, we're going to go over the different variations of the circuits as well as the different nomenclature and subscripts. For example, on an AC circuit analysis, you'll see all the nomenclature in lowercase. And then if we're referring to the DC circuit analysis parameters, all of these subscripts will be uppercase. So something to be aware of on these future slides. For the AC circuit analysis, we're mostly going to focus on the three fundamental properties of an amplifier circuit: the gain, the input impedance, and the output impedance. Now the two illustrations below mimic a two-port model, but it has your input impedance, your output impedance, and your gain. So the models that we're going to look over in the future slides are going to mimic this very crude illustration you see below. So what's the overall goal we're trying to achieve here? We're going to take a BJT circuit, for this one it's a common emitter circuit, and we're going to convert it to the AC equivalent model that you see to the right. Our goal is to simplify that one circuit down to the AC equivalent model, and then we can plug and chug and find answers based on this model. So one of the questions you're thinking is, why are we doing this? The AC equivalent model represents the BJT circuit as it behaves with an AC input. In the previous lesson, we tore apart all the AC elements of that circuit and we just did a DC analysis. We got all the DC parameters, but we didn't input the AC input back into the circuit and do an analysis. This is the other half of the coin because the AC circuit is going to act as a different beast compared to the DC analysis. And that's what we're going to go over today. Like previous lessons, we have steps. So step one, complete the DC analysis, meaning we have to obtain the DC parameters. And you're going to notice if you have the DC parameters, if you have uppercase subscripts. For example, if you look below, I have current for the base, current for the collector, current for the emitter, the B, the C, the E, all in uppercase. So if you have those, you have your DC parameters. Now, normally in some questions, if you're asked just to find the AC equivalent model or AC analysis, usually these are given. However, you have to be aware you have to find those parameters first. Next, you're going to short all your capacitors. In an AC equivalent or AC analysis, your capacitors act as shorts. Since that's the case, short them all. Next, you're going to place all your DC sources with grounds, which that one's pretty easy. We'll go over that in the next slide. Then we're going to simplify the circuit, input the AC equivalent model, and then plug and chug. And I'm going to show you this as we go on. Okay, so you're asked to perform an AC analysis on this BJT circuit. Now it's very likely you're given the DC parameters. So next steps are to short and ground steps. So we have a circuit, step one, all the way to your left, and the first thing we do is short all the capacitors and ground all the DC components. And then you're able to simplify it as you go on. So all you're doing is relocating your resistors and how they're viewed according to the BJT. And in a sense, you're just making it easily to visualize as you go through these steps. Now, once your circuit is simplified down, such as step 4 here, all you have to do is input your AC equivalent circuit. Now, the AC equivalent model here is one that was taken from the FE handbook. Now, you can use ones from your PE references or any of your previous college textbooks, but keep in mind the models are going to look similar to what you see to your right. Okay, the rest of the material is where it starts getting really interesting and complicated. Now, some of your textbooks, PE material, is going to have various different models as far as how they may be laid out or how their nomenclature is given. So I provided the T model and the hybrid model. Now in a sense, you're going to be using both these models at once, but keep in mind some textbooks will divide them up as you see right here. Now I provide the equations to the right because some of those equations only work for the T model and some work for the hybrid model. But just be aware these are how they're laid out. Now also some of these subscripts may be different in some books. These are the ones I'm going to use, and I'm going to try to keep it consistent throughout all these problems. Now, if you're going to visualize a model with both the T model and the hybrid model incorporated into one particular universal model, it'd be the one given to the right here. This is one put together that's going to visually give you a representation of how these equations are used. So you can actually see RV is not your emitter resistor, it's the resistance at the emitter. It's not the same thing as if you had a resistor in there. This is internal resistance. So everything in the gray area is the BJT, what's internal to it and its parameters. Everything outside the gray box would be your actual circuit, would be your R1, R2, collector resistor, emitter resistor, load resistor, all of those. So keep in mind, everything in the gray square is internal to the BJT, and a lot of these equations are based on just those parameters. Now, this particular slide gives people headaches. A lot of people have a problem with the two-port model when it comes to the hybrid model, because the H parameters are sometimes confusing on how to calculate them. But I know where there's a two-port lesson. However, this one needs to be focused more on the BJTs because the hybrid model is focused more on the BJT model. There's a lot of overlap for this particular slide. So if you look in the bottom left, I have HIE means H11. These are the same things. Again, I'm going off two different books here and what the nomenclature is. I'm showing them both. That way you're aware they are the same thing. It's just some books have a different nomenclature. Now the two models here, right here is the BJT. It starts with the base all the way to left. I have my emitter in the same spot and my collector. This is a just different form of the model that you saw earlier when it comes to the AC equivalent model. But later on, we'll show you how to do one of these in an example. Out of all the slides, this one might be the most important. We're going to go over a few items here that most textbooks either don't go over, overlook, or just kind of consider something as common knowledge. All right, first thing, if early voltage or R sub O is not given, just go act as R sub O is not even there at all. That's that output impedance or output resistance. So early voltage is usually given. It's not usually calculated. If you don't have that, they should at least give you output impedance, R sub O. It's usually a very high resistance. It's usually somewhere around like, it could be 10K and so on. And usually if it's that high, you can almost act like it's not there when it's in parallel with low resistance. So if you have a 10K ohm resistor and a 1K ohm resistor, your resistance is going to be close to 1K. So usually a lot of your equations and a lot of your books may actually act as if your output impedance is not even there, your R sub O. Next, your amplifier output will be 180 degrees out of phase from your input. So when we do an AC analysis and you input a waveform, it's going to be 180 degrees out. So just be aware when you actually perform your circuit analysis, they show you waves, it's going to be out of sync. Their gain and all that's going to be the same. However, it's just going to be out of phase. Next, you'll see R sub U. It is typically not given nor measured. R sub U is that resistor in the center. Again, it's very, very, very rare to see that, and it's usually very high resistance. Hence why in some of your models, you'll see a gap there or a blank because the resistance is so high, it's acting like it's not even there. But be aware, it is there, and there isn't an equation for it that actually lets you find your voltage ratio, and that's R pi R over R sub U. I'm presenting to you right now, that way you know it does exist, it is there, but it's very rare you'll see a circuit analysis with that being there. And just like I said earlier, your textbooks and references may actually have mismatching lettering and symbols. So you may have a model just like you have in front of you here with all different symbols and different lettering. However, how you calculate them is still the same. I try to use the most common ones in this lesson, so hopefully it should be able to get you through some of these problems. All right, so we're going to start with a really good example where the rubber meets the road. This example has been taken from the first video where we did a DC circuit analysis. Since we did a DC circuit analysis, we now have those parameters. And we're going to use those same parameters in the same circuit and continue on, but we're going to perform the AC circuit analysis. So we have this one circuit right here. This is our collector, emitter, and amplifier. Nothing new, it's very common. And we're going to follow the same rules as we did in the PowerPoint. Step 1, obtain the DC parameters. Done. Step 2, we're going to short our capacitors and ground our DC sources. So I'm going to go ahead and make a copy of this. Let's go ahead and short our capacitors. So what I'm going to do is I'm just going to, so just make it easy, I went ahead and remove the capacitors, short. All right, and then we're going to ground our DC source. Okay, that should be your first steps when actually simplifying down the circuit. Now when you do that, it's going to move this resistor down here to the ground. If you want to just visually represent, give you a good visual of how it should look, we can move all these resistors around to make it more eye appealing and easy to do a circuit analysis. So what I'm going to do is I'm going to take the same circuit and I'm going to bring all these resistors down to the same ground. That way it's easy to see. 2 seconds. So all I do is move the resistors down and made this circuit a little bit more easier on the eyes. So I still kept my input resistance and my input voltage. And all I do is just move a few of these things around. Now notice that you don't see an emitter resistor anymore. This one has been removed due to the fact that a capacitor has been shorted. So be advised that has been removed when you see those capacitors. They always act as shorts when performing DC analysis. Now, if you're curious why, by the way, if you do a Z for a capacitor, it's 1 over 2 pi, and that's FC. So if you have a frequency that's, I don't know, we'll say 60 hertz, and then a capacitance of 1 microfarad, it's going to give you an extremely low resistance. And I'm extremely, maybe a couple ohms. So be advised, that's why they're considered shorts, because they're almost minute to nothing as far as a resistance value. Anyhow, moving on. We have R1 and R2 in parallel. Then we have RC and RL in parallel. Just by using simple calculations, we could say 2K is in parallel with 1K, and then 10K is in parallel with 5K. Plug and chugging those in our calculator is going to give us 3.33 kilo ohms. And for this one, it's going to be 666.6 ohms. Okay. Now what we can do is we can go ahead and combine those two and see if we can simplify this down to make it more eye appealing. So let's do that real quick. So we simplified the circuit down one more time and just got rid of those resistors. Now we should be able to put this in our small scale model. That way we would start performing our AC analysis. So let me get that in there. Now right here, I've taken one of our models from our slides. This is very similar to what you're going to see in all your books. The only thing I added was RV down here. That way you could see where it's at. Now again, this is not your emitter resistor. This is just your internal resistance for your BJT. So we can probably start plug and chugging these in our models now. So we want to find gain. That is A of V. Because the gain of current is our beta, which is 153. So this one is inferring to voltage gain. All right, and voltage gain is found by R sub L over R sub V. Well, let's see what we need to find first. We can find R sub V very easily, our internal resistance for our emitter. So now our voltage temperature is 0.026. Now in the slides, we did a big calculation and it was 0.025 and some change, and you round up to 26. This was taken at 300 degrees Kelvin. That's very average room temperature. Some of your books may have 0.25. Some of my books had 0.26. Whatever one you use, you're going to get a very similar answer. So be advised, either one of those will work, hence the it's close enough sign. I'll tell you what, I'm going to get rid of this circuit right here just so I can make room. So I have R sub V equals our voltage temperature and then our emitter current. Now this is DC because notice how it's uppercase. Since it's DC, uppercase, we already were provided those. Hence why you have to find those early, because some of these equations have those DC parameters that are required. So this one's going to be 0.026 volts over, and this is going to be our emitter current, which is 0.234 milliamps. And then once we plug and chug that in our calculator, 8.04 ohms. So it's pretty good R sub V. We have R sub V. Now we need to find our output resistance. That's R of L, output impedance, and it's in parallel with your output resistance. So now right now, since I was not given early voltage, nor did I give you the output impedance, you have to act like that resistance is not even there. You have to act like it's so high, it's almost equivalent to that. So all we need is this number right here, our output resistance. Because if I didn't give you this information, you have to act like it's not there. It's just that simple. So that's pretty simple. R sub L equals 666.6 ohms. That was a very simple one right there. Okay, since that be the case, we can plug and chug it in our gain equation right here. So it's going to be, I'll tell you what, write it out. Gain equals R sub L over, and this is our internal emitter resistance, which is little r of sub E, and that's going to be, my pen will write, 666.6 ohms over, 8.04 ohms. And that would be our gain, and plug and chug that in our calculator. 82.91. And that right there would be our gain. So for number one, and I'll just put over here, we have a gain of 82.91. Okay. Now number two, we're going to remove the collector emitter capacitor and find the gain again. We're going to remove the capacitor from the equation, which means our emitter resistor is no longer shorted. It's actually in the equation. So let me go ahead and erase this. And what we did instead was we went ahead and took this guy and took him out of the equation completely. So if we remove this from our circuits, it looks like this resistor is now back in play. We're adding R sub V right there, because now you have that little R sub V right there, and now it's in series with capital RV, which is our emitter resistor. So that's pretty good. So we can use the same parameters we have here, except we're going to change up this equation just a little bit. So our gain is no longer just our output resistance, R sub L, over our internal resistance. Now you have to take into account the external emitter resistor, so R sub V. So that's where things change. Be aware, that's why I want to show you this model. That way you can see how things work. So visually, internal resistance is right there, as well as your external one. Because on some of your textbook circuits, they won't even show this guy. They'll just put their resistor right there, the emitter resistor right there. However, I'm showing both right now, since that way you can get a visual idea of how this works. So now we can calculate our gain, which is 666.6 ohms over, and this is going to be 8.04 ohms plus, now that we have this resistor back in play, it's 1K. So, and we can plug and chug that in our calculator, giving us an answer of, so our gain has been substantially reduced to 0.661. Wow. Just by that one capacitor being removed, our gain has completely dropped. In fact, it went the other direction. It's no longer gain, it's a loss. So our answer for number two is 0.66. That's pretty good. The really good thing about this model, it shows current flow through the BJT. So notice how we talked about how current flows through the base, down the emitter, and then from the collector to the emitter. Same thing happens here. Goes to the base, to the emitter, and then from the collector to the emitter. Now you can visually see the current flow as far as the AC circuit analysis. So it's very similar to DC, however there's a few equation differences. Now that we have the voltage gain, you can actually put back the 50 millivolts with the 1 k ohm resistor and start finding out what the output voltage would really be, just based on now that you have a gain. Okay, let's do another problem. This one, I already provided you with a two-port model with the H parameters as well as the output resistance. So these H parameters do fall within range of their typical values found in most of your textbooks. I did provide these typical values. That way, when you start analyzing these circuits, you have an idea of what they should be as well as how they behave, which I'm going to explain more in just a minute. Okay, so for this particular one, we want to find the output voltage, V2, and then we want to find the gain. Okay, these are very simple. And I also provide you the two-port equations as if you want to do the two-port analysis. I'm not going to get into that too in detail right this second, but let's go through this little by little. Okay, so I have R sub L, 100, so let's put that right there, 100 ohms. I have our input resistance, 1 kilo. I have our reverse voltage ratio, which is 5 to negative 4. I have our beta, which is 100. Just for the record, in case you didn't know, that's beta. I have our output impedance right there, which actually comes out to our output resistance of 10K. So just as a little healthy reminder. So that's how I came with 10K. All right, so we can actually start doing a circuit analysis of this bad boy, see if we can find V2. Now keep in mind, I'm going to do a few tricks just to get a ballpark estimate for good reasoning. 1, speed, and 2, it's going to be pretty close. All right, so I have our input, which is 1 volt, so V1 equals 1 volt. I have R sub n, 1 kilo. Goes through another voltage source, which is V2 times 5 to the negative 4. Now, the real good news behind this, you can make assumptions. Since this number is so low, like anytime you multiply a number times 5 to the negative 4, or any of these low numbers, it's almost equivalent to 0. Sometimes this parameter is going to be very close to 0. Some of your books even may refer to it as H12 equals roughly 0. So right now, I'm going to do a little bit of cheating and say that's 0 for the sake of argument. So I'll make it easy on me. To find my input, or my input current, it's going to be 1 over 1 kilo, which is going to give me 1 milliamp. So I was able to find I1, even acting like that reverse voltage ratio is not even there because it's so minute. So I'm going to write this to the side over here. We'll say I1 equals 1 milliamp. Well, let me clean this up. By me finding that 1 milliamp, I can find I2, because I2 would equal our beta, or actual current gain, times I1. Well, I know my current gain is 100. That's beta right there. So I2 equals our beta, or in this case, it's going to be H21 times, and this is I1, so it's going to be, in this case, 1 milliamp. So it's 100 times 1 milliamp. And that's pretty simple. You don't even need a calculator for that. You just move the decimal point over. So it's going to be 0.1 amps. So I sub 2 equals 0.1 amps. Nothing connecting these two together. You have to consider that independent of this one. So you have to find the parameters for this side, and then it'll start giving you the parameters for this side. So consider, just do one step at a time. And that's all I'm doing. I found I1. Now I was able to find I2 by finding I1. Okay. So now I know the current going through this guy right here. Well, I know the resistance right here, and I know the resistance right here. So it's pretty simple. Let me clean this up real quick. So V2, or in this case, the voltage at the load resistor, equals, this is going to be 0.1 amps, because that's our current going through this guy right here, this current source, and it's going this way. But it's got to go through our internal resistor as well as our load resistor. So it's going to split off. Luckily, that's 10K and that's 100 ohms. So there's going to be a substantial difference there. So to find it, this is going to be our 10K ohm resistor, internal resistance, in parallel with our 100 load resistance. Okay, because since these two are in parallel, we got to find the total resistance of those two. So V2 equals 0.1 amps times 99.0 ohms. And then if we multiply that times 0.1, it's going to give us an output voltage of 9.9 volts. So right at our load resistance right here, it's 9.9 volts, just based on that current. Keep in mind, these aren't exact numbers here. These are pretty close. Now, when I said earlier, this reverse voltage ratio is going to be very close to 0. Well, let me show you why. So right now it says V2 times 5 to the negative 4 gives us our voltage ratio. So if we want to look for that, it would be 5 times 10 to the negative 4 multiplied times 9.9 volts would give us 4.95 millivolts. So it's pretty close to about 5 millivolts. That's going to be subtracted from the 1 millivolt. So if we did that, would be using close to 0.995 volts. So again, it's very, very minute amount of voltage that's in the reverse direction. Since that be the case, that's why it's equivalent to almost 0. Doesn't mean it is, it just means it's pretty close to find the answers to the problems. This is kind of a cheap way of doing it. Now, we need to find the gain. Well, it's pretty simple. As we stated earlier, beta would be our current gain. Our voltage gain would be V2 over V1. That's our gain. So 9.99 volts over 1 volt gives us a gain of 9.9. So our gain is 9.9. Very simple. And again, like I stated earlier, sometimes some textbooks don't even give you this value because it's usually so high it didn't matter. For example, I had 100 ohms right here, and we came up with 99.0 ohms. So it only accounted for 1% difference, very, very minute amount. So even if I didn't take this into account, I would think it would be very close to 10 volts, which 10 volts, 10 over 1, our gain would be close to 10. So even if you rounded this, it would be 10. So just keep that in mind. There's ways that there's reasons the models kind of neglect some of these items for speed and to give you at least rough ideas how things work. So you'll see a lot of this when looking at some of your textbooks. Okay. So hopefully I provide you with enough information to be a little dangerous and maybe to at least get the ball rolling as far as going through some of these problems. I only went over the common emitter circuit because one is the most popular, easiest to explain. You can use these same models when performing the other circuits. You just have to move the arrows accordingly. So some of them may be pointing up and some of the polarities may change. So be aware, depending on whichever circuit you're trying to perform an analysis on, just make sure you have the right model. Principles still apply. All right. Well, I hope you all have a good evening, and if you have any questions, let me know.